Math Humans. We're going to do B2 today. We're going to be talking about multiple representations of functions. Our objectives are that we're going to determine whether a relation is a function. We're going to find multiple ways to write a function, and then we're going to talk about increasing and decreasing. So as we get started, remember from yesterday that a relation is a set of ordered pairs, okay, and that a function means that it is a relation where every x is unique, okay? When I think about functions and relations, I tend to think about rectangles and squares from geometry. A rectangle would maybe represent our relation, and then a square would be the function. A square is always a rectangle, but a rectangle is not always a square. Same thing here. A function is always a relation, but a relation is not always a function. So the primary way to tell is that every x is unique. So let's say I had z is my relation, and it was 1, 2, here comes those really creative numbers again, 3, 4, and 5, 6. Z is going to be a function because every single x is unique. So then what if I had G is equal to, and its ordered pairs were 1, 2, and then 1, 4, and then 5, 6. The ones repeat, it can't be a function, therefore this one would be just a relation. All right, so we can represent functions by putting them in set notation. We can also represent a function in a t-chart or a t-table, whatever you have called them in the past. Typically, we would write x and then f of x or y. And so if I took the one that I had for z, it would be 1, 2, 3, 4, 5, and 6. Again, my really creative numbers. And then this would be a function because, again, all of my x's are unique. None of them repeat. And then if I had x and f of x, which is the same thing as y, put an equals there so I'm consistent, and I had 1, 5, and 1, 2, 6, and 4, these two guys repeat. Therefore, this particular function is not a function, and it would be a relation, okay? Sometimes you'll see tables reported sideways. I tend to write mine sideways because it takes up less room on my paper. So I would do 1, 2, 3, 4, 5, and 6. It doesn't matter which way they are turned. I typically do this just because it takes up less space on my paper, but either way is fine. Okay? A function can also be represented as a graph. Okay, and we are going to be using our graphing calculators. If you don't have a graphing calculator, there are lots of free apps that you can get on your phones, both for iPhones and non-iPhones. You have to have a graphing calculator for this course. So if you do not have access to a grapher, and it doesn't matter which flavor it is, TI would be my preference, but I can't help you with a Casio, but I can with a TI. And I know that there are lots of TI graphing calculator apps. If you go to the App Store and just look, you can find a calculator so that you'll have one at your disposal. Alrighty, so if I want to represent a function graphically, then maybe it looks like this. So if I want to determine if it's a function or a relation, and I'm looking at a graph, I'm going to do that by the vertical line test, which is really very simple. So if I take and run a vertical line through my graph, it can only have one point of intersection on each vertical line. If it has only one point of intersection per vertical line, then we know that it's a function. So it's going to be a function. So let's say I had a different graph. So here's my cool graph. I typically, when I'm graphing, put an arrowhead on 2, and that's it. And let's say this was my function. Okay, nice absolute value function, but we don't have to be worried about that right now. And I run vertical lines through my function. Each line only has one point of intersection, therefore this would be a function. Okay, let's say I did a different one, and I had, this was my graph. Okay, this is a square root function, again, not important. But if I run a vertical line through the function, notice that I have 2 points of intersection. Therefore, this one is a relation. It is not a function because it has 2 points of intersection on that line. And then another example would be, what if I had the graph of a circle and then I ran a vertical line through there? Again, a circle is cool, especially on your grapher, but it's going to be a relation and not a function. So we always can recognize whether a graph is a function or a relation by whether or not it passes the vertical line test. Alrighty, the next thing that we want to talk about is an increasing function. So the definition of an increasing function as the x values get bigger, then the y values also get larger. Okay, so that would be your definition. Here's what it's going to look like. So if I have a function, let's say it looks like this, as my x values get bigger, my y values are getting bigger. Okay, another way to think about it is the slope of the graph is positive, and so this would be an increasing function. Okay, it can look like maybe this situation. So let's say I have the graph of the square root function. Again, the name of the function is not important, but as my x values are getting bigger, my y values are also getting bigger, which means that this would be an increasing function as well. And again, since I did it over here, the slope of this is kind of positive. It's going to get bigger slowly, but it's still getting bigger. Okay. I have one more example of a graph. So let's say I had this function. Okay, kind of cool looking, right? But as my x values are getting bigger, notice that my y values are also getting bigger. So that means that the slope is positive down here and the slope is positive up here. So this is also an increasing function. Sometimes when we talk about increasing functions, we look at it in a table instead of a graph. And that's okay, because a table is just a numerical representation of a graph. So let's say my numbers were 1, 2, 2 and 5, 5 and 10, 10 and 13, and then 12 and 19. So my x values are getting bigger. So my x values are getting bigger. And notice that the y values are also getting bigger. Therefore, since x is getting bigger and y is getting bigger, then that means that this is an increasing function. Okay, so that's kind of cool. So if we talk about increasing, that means that we also have to talk about decreasing. So for a decreasing function, the rules are the exact opposite. As the x values get larger, then the y values get smaller. Okay, so as x is getting bigger, y is getting smaller. So that might look like this situation. So here's going to be my function. Okay, so my x values are getting bigger, and notice that my y values are getting smaller. So this would be a decreasing function. Okay, another example might be the bottom half of a square root function. So maybe it's this guy. So as my x values get bigger, notice that my y values are getting smaller and smaller. So this is a decreasing function. Okay. What if I had the cube root function that had been changed a little bit and it looks like this instead? Okay. Notice that as x is getting bigger, the y values are getting smaller. So this is also a decreasing function. Okay. And just to show you that they don't always have to be all of one or the other, this is just kind of a cool little example. I could have a function that does something like this. This part is increasing, this part is decreasing, and then this part would be increasing. So functions can either be all decreasing, all increasing, or it could be a mix. This course is going to focus on these, but this is kind of interesting to think about. If I did it in table form, so if I had x and then here's my f of x, and maybe I have 1 and 20, 2 and 15, 5 and 13, 10 and 11, and then my last one is 12 and 6, notice that x is increasing, right? The numbers are getting larger. And then notice that the y values are decreasing, so they are getting smaller. So therefore, this particular function would be a decreasing function as well. All right, my dears, that is it for today. Make sure that you scan your notes and upload them into Canvas, and I will see you soon.